Next talk is Fabio talking about deep learning on HopsHadoop.
So hi everyone, I'm Fabio. I work for a company called Logical Crocs. We are a startup based in Stockholm, and we are the leading company behind the HopsHadoop platform. And today we are going to show you how you scale deep learning workloads on our platform, basically. So a bit of a step back. The project was born like a couple of years back with HopsFS. HopsFS is basically a fork of Apache HFS. The difference between HopsFS and the main difference between HopsFS and Apache HFS is that we took the metadata of the file system, which in HFS are stored in the name node, and we put them in a distributed in-memory database. And this allows us to scale both in terms of like space and like files we can store, and in terms of throughput. Just to be clear, this is not like some random vendor numbers. We actually these are like research and with like recognition both from academia and the industry. So on top of that, so on top of the file system, and actually we also have a fork of YARN, which is like the Hadoop resource manager and cluster manager. We fork it because right now YARN doesn't support like scheduling of GPUs. It's coming in a couple of next releases, and we do have it in Ops YARN. On top of like HopsHadoop, on top of HopsFS and Ops YARN, we build like an entire platform, and you can find basically everything, all the software you will expect from a big data platform. But we also want to provide deep learning solutions, so we also have the support for TensorFlow. On top of that, we have Jupyter and Zeppelin to write your code, and the whole platform is organized basically in projects, and you can think about like GitHub projects. So you have like users can collaborate on multiple projects can like have data shared like across different projects, and so on and so forth. Everything is just like a REST API, so you can build your own applications on top of HopsHadoop. And we just released the 0.3 version, so you can go and check it out. I will have a link at the end of the slides. So as I said, we want to provide like deep learning solutions, and when it comes to deep learning, Python is basically the winner. We allow people to run deep learning on HopsHadoop by using conda repositories. Basically, each project has its own conda environment. Each like users can install on their project whatever libraries they want, and then they will be able to like use those libraries from Spark and from TensorFlow, and we see later that these two are quite connected. Besides that, we develop our own Python library that surprise is called Ops Python library. And the thing that this library does a bunch of stuff. The main thing is that it allows you to like do hyperparameter searching for your models and manage the TensorBoard lifecycle. I will show an example later how you can do that. Now you have the platform, you have all the tools, you have maybe some good ideas, and we develop this thing as actually like a PhD student working really hard on and getting this tool done. It's basically Data. The idea of Data is that you organize your clusters, your ops cluster in a peer-to-peer network, and they can basically exchange data sets with each other. And the idea is that if you, let's say you have like your new like image recognition neural network and you want to try it out, you can go on the network, grab ImageNet, and then you are good to go, and you can start training and start seeing how good is your network. Or on the other hand, if you have like a cool data set, or you did like a cool experiment, you can like register the data set with the network, and then people can start using it and start doing more experiments basically. The nice thing about this is that the whole protocol is based on UDP, and the idea is that we don't want to impact like production traffic going on your cluster. So the tool listens for like traffic on the network. If it is empty, then start transferring the data set. Otherwise, it just backs off and let your production traffic going on. So you do have your platform, you do have your data, and then you build your own model, and your model will have probably like hyperparameters, and you want to look what is the like good combination of hyperparameters to use the right combinations. What you can do is you can do like hyperparameter searching in parallel with the Ops Python library. The idea is the following. You take your TensorFlow model and you put it into this function. You define some like a dictionary of values of saying, okay, I want to test these learning rates, I want to test these dropout values. This is actually optional. You can say, in this case you say, okay, let's try like a grid, and so let's try 001, 045, 0005, 045, and so on and so forth, like in the grid manner. And then you import this TF launcher, which comes down with the ops library, and you say, launch this model with this grid. And what this basically does is the following. It uses Spark to go to Yarn and request like 6 different executors in this case, and will launch your TensorFlow, the TensorFlow model, and run your TensorFlow model for you on the cluster. The nice thing is that Spark is now aware of like that can go to Yarn and ask for GPUs. So your model, like your all experiments, can be run on one or multiple GPUs basically. Besides that, TensorFlow launcher will actually launch for you like a TensorBoard, which is basically, for those of you who don't know what TensorBoard is basically like a nice visualization UI where you can basically track like how your experiments are going. And so on the end of the execution, you will probably see. And so let's say you were tracking the accuracy of the model, you will be able to see which of this combination of hyperparameters gives you back like the best accuracy basically. Now, you have your model, you have data, and so on. Now you want to like really like scale out in the sense of like you want to go like distributed training and train on the full size data set. Now, when it comes to distributed TensorFlow is actually designed to be used with like a cluster manager. You have to start all the processes. You have to tell each process where all the other processes are, and so on and so forth. So you either want to use Kubernetes, Mesos, or in our case, as we are in the Hadoop world, we use Yarn again. And we exploit basically the same fact that we were doing before with TensorFlow Launcher, and we use Spark to actually distribute the code, allocate the resources, and start the processes for you, basically. We use a tool actually open source by Yahoo. It's called TensorFlow on Spark. And the idea is that Spark is used to, as I said, request resources from Yarn. It's used to start the processes, and it's used also to distribute your code to all the workers, basically. We actually forked the TensorFlow on Spark, mainly because, again, Ops Yarn supports exclusive GPU allocations. So you basically, like, this our version of TensorFlow on Spark can request GPUs, basically, for you. And there is another, like, a minor improvement, well, minor, not really minor. The idea is that parameter servers, which are effectively like Spark executor, will not get the GPU because they don't need it. So it's like a waste of resources, basically. And again, TensorFlow on Spark will manage for you the TensorBoard, basically. This is how basically you run everything. Again, you wrap all your model inside this training function. Inside training function, you call this TF node, start cluster server. This will give you back like an object telling you, okay, am I like a worker, am I a parameter server? And then that you take action, basically. And then you call this TF cluster. You basically give you the Spark context. Give you like you have to give like the training function, the number of executors, and the number of parameter servers you want. If you go on this link, like there is like official guide from Yahoo telling you how you can transform like normal TensorFlow code, normal distributed TensorFlow code to the TensorFlow on Spark. Now, the problem is that when you are scaling out the sense of like you are training with a lot of GPUs, thank you, the parameter server architecture doesn't really scale because especially if you have like large model like VGG16, which I think the weights are like 500 megabytes, something like that. Network becomes a bottleneck. Every worker, every GPU has to communicate with the parameter server at the end of each iteration. So you really can't scale, basically. These are experiments done by Uber. Uber wrote this tool called Autobot, and the idea of Autobot is the following: they actually built on top of like work done at Baidu, And the idea is that you don't have like a centralized architecture, but you have like you organize your workers in a ring, basically. It's data parallelism, so each worker gets his own batch of data you want to train. And the idea is that when the work is done, the updated gradients are distributed through all the workers using the all-reduce algorithm. Just a quick recap of all the reduce algorithm works. Basically, you have like these 3 GPUs, let's say, and you have like your gradients, let's say, and you divide it in 3 batches because you have 3 GPUs. And the idea is the following: synchronously, GPU 1 submits to GPU 2, GPU 2 submits to GPU 3, GPU 3 submits to GPU 1 again. You do that twice. And at the end of the first round, the first two rounds, you will have like one GPU that has like each GPU has one of the chunks of the gradients that it has to transmit in the final state. You do another 2 iterations, and you have every GPU has the updated gradients for the next iteration, basically. But as I said, this is like a synchronous protocol. So before the next iteration, all the transmissions has to be completed, and this means that you want to have like as homogeneous as possible GPUs and as homogeneous as possible a network. So let's say you have like 10 links, and you have like 9 InfiniBand and 1 Ethernet. Then you're wasting InfiniBand because all the workers will wait until the transfer between the 2 worker connected through Ethernet are finished. One optimization you can have in this system is the following. So if you have like a neural network, and then you are doing like the computing the errors, basically, the gradients update for the last or the external, so to say, external layers are available much earlier than actually the gradients update for the first layers. So you can start transmitting the gradients update for the last layers before actually having computed the gradients for the first layers. So you can get more performance, basically. So this is how you use it. There is like a full support for all-reduce on HopsHadoop, basically. The idea is the following. You write a Jupyter notebook, including all your code. Again, you have to do some minor modifications to your code. One of the things is you have to feed your optimizer into this over-distributed optimizer. And you have to tell, well, each worker the position in the ring, so he knows to which other worker it has to send the gradients and from which worker will receive the gradients. You wrap everything in a notebook, as I said, and then from another notebook you call this all-reduce launch Spark, and you give the notebook path. And this again will transform your notebook in a Python program, execute and train, and we show you the TensorBoard logging, basically. I do have like a quick demo of the whole platform. How much time do I have left?
5.
Okay.
6.
Which one is there? No. Do you know what? Yeah, I know, but there are like 4 of them. Not this one.
Did it die?
Oh, we can open another one.
You just put it again.
Yeah.
Oh no, it's in full screen, right?
Okay. Okay. So this is our we have like a production cluster with the platform installed, and what you can do, for instance, like you create a new project. Let's go like so. And the idea is that we don't need Hive, we don't need this one, and this one. Can I go out of the full screen? Yes. Nope. Control minus. Yeah. Okay. Awesome. So now we can, for instance, look for data. So we have a bunch of data sets up in the cluster. For instance, we can look for quick draw. For instance, This is like, okay, this is only 300 gigabytes. We can add this dataset to our project. This is going to be fast, like this is going to be immediate, just because the data is on the same cluster, so you don't have like the transfer to do. But if you were on a different cluster and you were going to this data service, you will be able to see the progress of the transferring, basically. So once you have your data there, what you can do is you go into the Jupyter notebooks. You say, let's say this TensorFlow, we say, well, I'm going to do like 6 Paragon experiments. Each executor for Spark will have 1 GPU, a bunch of memory, and you can start. So the first thing you want to do maybe is like doing the data, for instance, in the quick draw experiment, it's basically a JSON entries. And the thing is, what you want to have is that as you're using TensorFlow, you're using maybe expensive GPUs, you want to like minimize the time you actually spend doing preprocessing while training. So what you can do is basically, if you're using Spark, in this case I'm using Spark, I'm like converting these JSONs basically into some into actually like a dataset of TF records. So it's ready for actually training. Then we can go to this one, which is basically the API parameter searching. So as I said, again down here you say, okay, define a dictionary of possible parameters you want to test. These parameters are then provided to your training function. Then you say, okay, these are the model parameters, and you can test with different dropout values and different learning rate. We can actually run this notebook. And it will take a while to get up. So the TensorBoard explicitly. This one. This one is the TensorFlow Spark notebook. We have like here we have like how to ingest the data. You are reading the tensor, reading the TF record subsets. These are like the dataset APIs, which are really cool from TensorFlow. This is the model. And then down here we have the basically the call I was talking to you before, saying, okay, tell me if I am a server or not. You can ask, say, okay, just wait for it, otherwise start the process and start training. Here is me not really super a pro in writing TensorFlow code. It's really ugly, but let's just skip here. And this is like how you basically run. This utils basically comes out of the ops library. Say, okay, this is like a number of executor you ask, and this is a number of parameter server you ask for, and you start the training basically. Say, okay, this number of executor again. This is say, okay, I want you to start TensorBoard for me, and this is the input mode. You will find like more in documentation. And finally, we have like the Oliver notebook. Again, same code before, the network ingestion of the data. Here's the one. Here's the thing I was telling you. You have to specify basically in which position each worker is basically. Say, okay, this is my local rank, so to say. And this is a notebook to actually like that contains all the information and all the code itself. And then you have these notebooks that actually launches the whole train. And potentially we can see, yeah, we can see that here for instance the 6 experiments I announced before for doing API parameter searching. TensorBoard is up and is showing like some graphs basically. So I have to wrap up.
Second one.
Yeah. So that's it from my side. As I said, we released the 0.3 version of the platform. You can go on this link and get like a background machine, like a VirtualBox machine, so you can try it out. We have documentation for everything I said on this link. Please start us on GitHub if you want, and follow us on Twitter. Thank you.
Thank you, Fabio. Time for questions.
Thank you for the presentation. How the tools that scales with the number of GPUs?
Come again?
How how the tools scales with the number of GPUs? We're gonna
This one, this robot thing.
yeah, it's over that manage this.
Yeah, the idea, if you look back to this one, so the orange is the normal parameter server architecture for TensorFlow, and the light blue and the dark blue are all of us. The light blue is using TCP.
Okay, yeah.
The dark one is actually like lighter, darker blue is using RDMA.
Okay, thank you.
Any other questions? Going once. Twice. Yes.
Thanks for the presentation. Would it be suitable to use this kind of approach to run a single machine with multiple GPU on it, or would you advise to use it more to have multiple machines?
Okay, we are actually having like one single machine. We are adding another one, for instance, with like 10 GPUs each and running Autobot.
Okay.
But yes, you can potentially scale to multiple machines.
Okay.
I think there was a paper, I think in June, from Facebook. They were like reducing training of ImageNet to around, I think, less than an hour. I don't remember exactly the time. And they were using the same approach, I think, over 256 workers, so 256 GPUs spread at this point on multiple machines, basically.
Okay, thanks.
One more? No? Okay. Thank you, Fabio.